Okay, not so. Let me share the screen. Okay, so yesterday we started our discussion on the semiconductor materials and how energy bands look or form in these semiconductor materials. And we want to do it with an example of silicon. Okay, so silicon is the electronic configuration as we know. It is 1s2, 2s2, 2p6, 3s2, and 3p2. And these 1s and 2s and 2p, so they are like the core cells, and therefore they hardly overlap when two silicon atoms come close. And only the most likely scenario where the overlap will be maximum will be for this 3s and 3p orbitals. So they will overlap when electron or when two silicon atoms they come closer, or when silicon atoms tries to form a bond. Now, but it doesn't mean that only there are two valence electrons that silicon has. Rather, silicon has 4 valence electrons. And how does it happen? So it happens because of the hybridization. So this 3s and 3p, so they will hybridize and they will form this hybridized orbitals. So here in the second picture, here it is all like their atomic orbital before hybridization. But after hybridization, so you have the formation of this hybridized sp3. So this is a sp3 hybridization takes place, and that leads to a formation of these 4 degenerate hybrid orbitals, sp3 hybrid orbitals, and each will have then 1 electron each. That means each sp3 hybridized orbital is half filled, and they arrange themselves in a tetrahedral geometry with a bond angle of 109.5 degrees. So this is what happens when the silicon wants to form a bond with any neighboring atom. So now, due to this 4 hybridized orbitals, so this silicon itself can form with a bond with itself. So silicon and silicon. So that is what happens in a solid. In the silicon, when you put all the silicon atoms together, so this is what happens. So similarly, you can also have silicon can also form bond with hydrogen as well. So that is also possible, where the hydrogen 1s orbital now will share 1 electron with the silicon, one of the sp3 hybridized orbital, and then you will have a silicon. So 4 hydrogen atom can have a bond with silicon. So very similar to what happens in case of methane. Now, so one thing is why this hybridization is possible? So one reason is when you look at the energy of 3s and 3p level, so there is not that much difference, and therefore this hybridization leads to so it forms 4 electron orbitals or electron state which are degenerate in nature. So that means they have all same energy. So this is why this hybridization happens. So we have the atomic. So this is I think a typical picture which you might have seen before as well. So when we talk about silicon crystal or solid, that you have these silicon atoms in the center, and then each now sp3 hybridized atomic orbital will contribute 1 electron. So you can say this is like you have 1 hybridized or you say, let's say, so each is contributing one electron, or sharing one electron with the neighboring silicon atom, and that's how you form this covalent bond. So you have the formation of the covalent bond, and uh, you form the crystal. Okay, and all this is in a tetrahedral geometry. Okay, so the crystal structure would look very similar to the diamond crystal structure. So this silicon crystal structure is similar to a diamond crystal structure. Okay, so the next question is then, how do we get a band, or this energy band formation happens in this crystal? So how the band is formed? So this is again we have. So again we go back to the picture like we saw earlier for lithium or for hydrogen. So we go back to that picture again. So what you see here, we have this 3s and 3p orbitals. So in the isolated atom, and we are neglecting the other orbitals because they are core shell, so close to the nucleus. Now these 3s and 3p, they will form this hybridized orbitals. So they will form this hybridized orbitals with this four hybridized orbitals, this sp3 hybridized orbitals, and they are all the same energy. So you have 1, 2, 3, 4 electrons. And now when a neighboring silicon atom, they come close together, so you have the same situation for the other silicon atom as well. So you have 4 hybridized orbitals here on for silicon 1, and 4 hybridized orbital for the second silicon, and this hybridized orbital will form a bonding and anti-bonding orbital. So this is now the kind of a molecular orbital that is formed out of this hybridized atomic orbitals. The earlier case we saw, it was only the atomic orbitals which are forming these molecular orbitals. But in case of silicon, the difference is the atomic orbitals first form the hybridized atomic orbitals, and these hybridized atomic orbitals then form this bonding and anti-bonding molecular orbitals. So the geometry again is the tetrahedral geometry. So now you have these bonding and anti-bonding orbital, and therefore you will have these electrons will go to this bonding orbital, okay, and then they will be shared with, let's say, so each hybridized orbital is forming a bonding and anti-bonding orbital, so with 1 electron, and then when it forms a bond, so the bonding orbital will have 2 electrons with 1 spin up and spin down, and the anti-bonding orbital will be basically empty. So now if you focus on only one hybridized orbital here, so let's look at this hybridized orbital. So this will form a bonding and an anti-bonding orbital. This is a molecular orbital. This is an anti-bonding MO. And now, so this is 1 electron, and the next electron will come, the other electron will come from the neighboring silicon atom, and they, so one will be spin up and spin down. So the bonding orbital will be full or completely occupied, and the anti-bonding orbital will be empty. So similarly, the same case will happen with all the other 3 hybridized orbitals as well. And so when you take, so this is like when we bring two atoms together. Now, if we bring n number of atoms, so what happens? So basically, this bonding orbital will further split into, depending on how many atoms are there. So this bonding orbital will form basically the one energy band, which is known as the valence band. Okay, so this, the bonding MO will form the valence band. So when you have n number of atoms, so n normally is like 10 to the power 23, like that. And the antibonding NO, so they will also split further, will form the conduction band. So you have basically these two bonding and anti-bonding this orbitals with different energies, and this each bonding molecular orbital or the energy will split again into n energy states when you bring n atoms together, and that will form your valence band, and the other one is conduction band. But now when you look at when you fill up the electrons, so valence band is definitely completely full or occupied, because your bonding molecular orbital is also completely full. So therefore, all the electrons you have in a solid in silicon will go to the valence band, and the conduction band will be, so this will be your empty, and this is your fully occupied. And what happens moreover, one interesting thing happens here. You have a gap between these two bands. So you have the formation of bands due to this. So first you have formation of hybridized orbitals. From hybridized orbitals, you have the formation of the bonding and anti-bonding orbitals. And those energy states, they further split and form the valence band and conduction band. And since the bonding orbital is fully occupied, so the valence band is also completely filled, and the conduction band is empty, and there is already there is a huge energy gap here as well. Okay, so this energy gap will still be there, and that uh, appears also in the when the bands are formed. And what is the energy gap? Energy gap is nothing but uh, like in, there are no electron energy states that are available within a energy gap. So that means electron cannot occupy any energy state, uh, or electron cannot have any energy uh, between this E. So this is your EV and or EV and ECB. So electron cannot have any energy between your EVB and ECB. So that means in a silicon crystal or in a material or semiconductor, so this Eg is your energy gap, and we can say, so this is the difference between ECV and EVV. So this is the bottom, and this is the top EVV, and this electron cannot have any energy between these two, or any energy with this value. Okay, so either energy will be up to EV, and then if it goes to conduction band, so it will have an energy of EC. So there cannot be any energy state within that. Okay, so before going here, so I want to also discuss few things. So one is So if we take example of silicon, so silicon has a energy gap of about 1.1 electron volt. Okay, so now if you take germanium, this value is 0.66 electron volt, and if you take gallium arsenide, for example, so that is around 1.43 electron volt. So this band gap that appears is different for different uh, materials. So it is uh, so depends on again what kind of atoms are there, which atomic orbitals are overlapping, and what is the energy difference between your bonding and anti-bonding orbital. So it is a very specific material property, this band gap. And this picture, what we have drawn here, so this, when we say that you have a fully occupied valence band and completely empty conduction band, again, this picture what we have drawn is at T equal to 0 Kelvin. So this schematic picture that we are showing here, it is at T equal to 0 Kelvin. But what happens if you increase the temperature? If you do that, so there is a possibility of excitation of electrons. So when your temperature is greater than 0 Kelvin, so you have a possibility of excitation of electrons. And remember, when you are at T equal to 0 Kelvin, so in this case, now there is no possibility of any conduction. So here, sigma will be equal to 0. Why? Because even if you are applying an electric field, so all the electron levels are full, and electron doesn't have any energy level to go to. Okay, so there will be no change in its momentum or anything, because this electric field, unless, since the valence band is completely full, so there is no electron state available for an electron that it can change its momentum. Okay, so each electron now is occupying an energy level, and that means its momentum is fixed, and all these states are fully occupied, and there is no empty states available. So therefore, at 0 Kelvin, your conductivity will be 0. Okay, and that is true for this all the semiconductor materials, where the valence band is completely full and your conduction band is completely empty. However, if you increase the temperature, so what happens? So if you increase the temperature, so there will be excitation of electrons from the valence band to the conduction band. So that is known as the thermal excitation. Okay, so this is what we call thermal excitation. Or thermalization, or due to the temperature. Okay, so another kind of excitation that can happen is the photo excitation. That means if you shine light, so then you can and the energy of the photon, incoming photon, so this energy HF, if it is greater than the band gap, so in that case you can excite one electron from the valence band to the conduction band. And now if you are applying an electric field, so these electrons in the conduction band, so they can move now. So when you are applying an electric field. Okay, so in that case your sigma will be, so you will have a finite conductivity and it will be non-zero. So therefore in semiconductors, so when you increase the temperature, so you expect that the conductivity will go up. Okay, so if you plot the conductivity as a function of, or we saw that when you plot resistivity as a function of temperature, so the resistivity of a semiconductor was going down. That means the conductivity goes up, and that is because you have you can excite electrons from the valence band to the conduction band, where in the conduction band these electrons can move or drift, let's say, due to the applied electric field, and you have a conductivity. Okay. Now, one consequence of that, when you excite the electron, so what you create is a empty electron state shown here, where you create this empty electron state, and these are known as holes. Okay, so what you create is these holes, and these holes, they are also, so they are like, you can say these are like absence of an electron in the valence band. So you create these holes, which are also very similar to, behave similar to electrons in terms of conductivity. So these holes, or H plus, that the symbol, so it behaves exactly like electron, only it moves in the opposite direction to the electron. So how this holes or how this hole can move? So normally what can happen, that one electron, neighboring electron, it can shift, okay, and then typically you say, instead of saying the electron hops from one place to one momentum state to another momentum state, or one energy state to another energy state, so you say that hole, this H plus actually moves to the valence band. Okay, and that is what normally what we say is they contribute to the conductivity in that way. And remember, this hole, this only exists within the solid. So you cannot find a hole in a free space, okay, or in vacuum. So in vacuum or free space, what you have is always electron. So only this hole, this concept of hole, that exists only within a solid, or basically in a semiconductor material. Now, since you have electrons which also contribute to conductivity, you also have holes which also contribute to the conductivity. So the conductivity is given by, for a semiconductor, so we saw earlier it is N. So let me write down it. It's NH, UH. So electron and hole both will have the same charge. And what we have is Ne is this number of electrons per unit volume, or number of conduction electrons. So this is number of holes per unit volume. So similarly, you have the mobility corresponding to both. So this is the electron mobility, and this is your hole mobility. So the total conductivity of a semiconductor is not just for a metal, it was just N E mu D. So mu D is a drift mobility, N is number of free electrons, and E is the charge. But here you have an additional charge carrier, which is your hole. So therefore it will also contribute to the electrical conductivity. So is Ne always will be equal to NH, or will it be different? What do you think? It will not be same. Why? If it is not same, then in which case it will be different? Yeah. So if you take a normal, just a silicon semiconductor, so what you have is the number of electrons will be always equal to number of holes. Okay, so if Ne is equal to NH, so that normally is known as an intrinsic semiconductor. So there are several definitions of this intrinsic semiconductor. So sometimes you can say number of electrons and number of holes are same, but what actually happens is number of electrons and number of holes will be same only if your excitation is possible due to temperature. Okay, so the thermal excitation, so that only will lead to a formation of same or give same number of electron and hole pairs. But if you have impurities or if you have doping, so yes, so if you have doping, in that case, Ne will be different from your, this number of electrons will be different from number of holes. Okay, so that we will see. So in that case, you will call it an extrinsic semiconductor. So that means you can have electrons in the conduction band uh, other than the thermal excitation. So this is here example is the doping. So now let's just divert a little bit before going to continue with the semiconductor thing. So just to complete the discussion on these band structure of different materials. So I want to okay. So let's take an example of like earlier we talked about diamond structure. So which we said it is due to the carbon-carbon covalent bond, and so it is very similar to that silicon. Okay, so however diamond is not not a semiconductor, it is an insulator, right? So what happens in case of carbon? So carbon is, again, if you look at the electronic configuration, so you have 1s2, 2s2, 2p, 2. So in this case, so the outermost orbital is the 2s and 2p orbitals. They are the outermost orbitals. So they will participate in the, they will overlap and they will form the bond. Okay, and now again you will have this sp3 hybridization, and that means you will have this hybridized orbital, sp3 hybridized orbital with 4 electrons. So these are all sp3 hybridized orbitals. And now this sp3 hybridized orbital, when a carbon-carbon atom come together, so these sp3 hybridized orbitals will overlap and then form the this antibonding and bonding molecular orbitals. So you have again a bonding orbital and an antibonding orbital. So this is your, we have this one sp3 hybridized one, and then so you have another sp3 hybridized orbital. So they will come and form a bond, this covalent bond, again very similar to silicon, and you have the molecular orbital which is completely full. And then similarly, when you bring such n carbon atoms, so again this will be again in the tetrahedral geometry, and when you bring all these carbon atoms together, so you will form the band. So this bonding orbital will form the or the antibonding orbital will form the your conduction band, and this is your conduction band, and this is your valence band. And again you have a band gap here as well, but this band gap is much larger. So this band gap in case of diamond is about 5.4 electron volt. So earlier in silicon it was 1.1 electron volt, but in case of diamond it is large due to this large band gap. So you have so you don't have any conductivity even if you are when T is greater than 0, even in that condition, so there is no thermal excitation possible, because the band gap is larger. So therefore, if the band gap is large, so those materials, so the semiconductor and insulator, in a way, when you look at the band structure or the formation, so they look similar, but the band gap is very different. And that's why you don't have any thermal excitation, and conductivity is not even not possible even at if you go to certain temperature. But if you go to really high temperature, most likely you can excite electrons and you will have certain conductivity. So in terms of the temperature dependence, the semiconductor and insulator will behave quite similarly, but the values will be very different. So to summarize all these things that we talked about, to differentiate between metal, semiconductor, and an insulator based on the band structure. So we can use a schematic like this. So when we say it is a metal, so let's say this is a picture of metal. So what you have is you have overlap of several atomic orbitals, and they form a band which where you have electrons filled up to the Fermi level. So you have this is, we say, a partially filled conduction band. Okay, that means this conduction band forms due to overlap of. So first of all, you have energy band due to each atomic orbital, and those atomic the bands that form due to atomic orbital, they will further overlap and form this partially filled conduction band. And so electrons will fill up from the bottom up to a level which is known as the Fermi level. Now in semiconductor, so what you have is so this is like one of the most familiar picture which you have already seen many times. So you have the conduction band, and you have you have the valence band here, and you have the conduction band, and then you have the energy gap EG, where no electrons can have any energy within that. So there is no electron state available within the band gap, basically. So you have the fully filled valence band and fully empty conduction band. So the same picture you also have for an insulator. So where you have your conduction band will be here, and the valence band will be here, and you have a band gap as well, but this band gap will be very large, and therefore you have no conductivity even when you go above the 0 Kelvin value. So this is like a typical schematic picture you must have seen many times before as well. And this comes due to this formation of energy bands, which is nothing but due to overlap of atomic orbitals or overlap of this hybridized atomic orbitals and so on. So it is closely related to the structure, how the structure or how the atoms are arranged, or how the bond formation takes place. And basically that is related to your electronic configuration of the material. Okay, so is it clear? Or any question? Okay, so if not, so one more thing which I want to discuss is something known as effective mass. Okay, so what is effective mass? So let's look at, so effective mass, what we are talking about, mass of the electron here. Okay. So why we are saying it is, I am coining this term effective mass. Why not just simply mass? Now let's look at one electron in vacuum, for example. Okay. Uh, so in vacuum or in free space. So that means the electron is not attached to any solid or anything. So now you are applying a electric field, which will, so then the electron will experience a force, okay, which is proportional to, or then it will be accelerated in that force, which is given by this expression F by m. So your acceleration in free space or vacuum would be equal to E by m. Okay, so that is quite well known. But the electron inside a solid behaves very differently. Okay, so it is, although when we talk about conductivity, we say it is a free electron. However, it is not really free. Okay, so it is nearly free. It is not completely free. Why? Because you have external electric field, which will give, of course, external force, but you also have many ions within that, even electrons and ions, and that leads to an internal, so they will experience an internal force which doesn't exist when the electron is in free space. So because of this ion and other electrons that are present in the solid, so they will also have some, so it is definitely they will have some electric field or force. The electron will feel that. So in that case, so your or I can write down, so the total force on the electron, so will be your F external plus F internal, and this external is due to the electric field you have applied, let's say. Okay, and this internal one is due to the ions and other electrons. So due to this internal field, so the total field is different. And what is the acceleration of the electron? Acceleration will be F total by the mass of the electron. Okay, so now this F total is consists of F external and F internal. Okay, so one can say that definitely you can say this acceleration of electron inside the crystal will be very different from the acceleration in vacuum, or so we can say this is vacuum or free space. Okay, so this is definitely different. It is not equal. Okay, so it is not equal to the acceleration in free space or vacuum. Now, how do we normally when we talk about materials, so we don't talk about this acceleration. So it is rather represented by, or you can combine and say this effect is in terms of, it will be reflected in terms of the electron's mass. Okay, so what to account for this internal forces, so we can say due to these internal forces, the electron will appear as if it has a different mass compared to the mass it has in free space. So the free space mass is, this m is normally 9.1 into 10 to the power minus 31 kg, right? Now this mass probably actually what happens, the acceleration and this acceleration is different. Okay, but this is normally represented in a way by saying that your mass of the electron actually changes. And so what you write, so in free space we write F external equal to ME into A. This is, let's say, vacuum, and this is in free space, okay. And in a solid, we will write a similar expression, but we will say that the mass of the electron is different, okay. So in a solid, so this is Me star, okay, and this Me star is known as the effective mass. So it appears as if there is some extra or the electron becomes heavier, or it can also happen that it also can become lighter compared to its free space mass. Okay, so this mass 9.1 into 10 to the power minus 31 kilogram that you observe, so it can be more or it can be less depending on what is the internal field it is experiencing. And this is most of the time this effective mass term is used in understanding the nature of electron, whether it is completely free or not. So this effective mass can be, so for example, if you take silver, okay, for silver, this effective mass is actually exactly similar to Me. So silver is a conductor, and if you look at most of the conductors, so this Me star will be equal to Me, okay, maybe a little bit different, okay. But if you take, for example, so on the other hand, let's say lithium, for example, this Me star can be 2.2 times Me. So it appears much heavier than free electron. And what is the consequence due to this effective mass? So if you look at and why we are interested in this parameter, because when we look at the conductivity, so we said conductivity is Ne into mu d, right? And what is the drift mobility? It is nothing but E tau by Me. So now the mobility depends on inversely proportional to the mass of the electron. So that means if the mass changes, the mobility will also change. So that's why this parameter is important when we look at when we want to know the conductivity or the electron movement in materials. So particularly this value can be very different in semiconductors. So in metals, it is not that interesting because we assume, or it is actually very close to the free electron mass. But in semiconductor, this value can be very different, okay? So let's say for silicon, for example, Me star is about 0.18 Me, so not that big difference. But if you take germanium, so this value is Me star is 0.56 Me. So even it appears lighter in germanium, and therefore the mu d will be large, is large in germanium, okay? Because of this, it appears the effective mass of the electron is much lower than its free, the value it has in the free space, okay? So we will we'll continue with this effective mass and some other interesting parameters related to energy band next week. So now, since I said we will have the quiz, so I will assign it, and then you can all, so the quiz will, so the quiz will be for 7 minutes, okay? So let me, assign it. So you can go to the Google Classroom. Now it is 46. So okay, so I have now assigned the quiz. So you can go to the Google Classroom and start.